Give me 1 second. That is, yeah, now it's streaming, live stream. So yes, Chris, please. I mean, we have now Chris continuing his third lectures on quantum simulation and quantum computing with atomic.
Give me
ions.
1 second. That is,
Oh.
yeah, now it's streaming.
Great. Now, excellent, Chris. Please go ahead.
Okay, all set to go. Okay, everyone. You know, it's hard lecturing remotely. It's anyway. I'm not. I like to see everybody's face, and the questions come more naturally. But what I've liked about this is that the pace has been really slow. It means I'm going to run out of time, but that's okay. So I wanted to. We were sort of in the not quite yet skiing down the other side of the mountain. We were developing kind of the background, the theory on how we use these dipole forces, these laser dipole forces on individual ions to realize an effective spin-spin interaction that allows you to entangle them to do gates. But when you do that, you're creating phonons as well in a transient sense. And then at the end of the gate, the phonons decouple and you're left with an entangled system. So I'm going to, these first 3 slides you already saw, so I'm going to go very quickly. But our basic light matter Hamiltonian was an interaction between a classical laser field and a collection of ions, and we're summing over all the ions I, and we're also driving motional modes. So we sum over all the modes M. These are coupled modes. They have resolved frequencies omega M with their creation and annihilation operators. And so this is a detuned spin-dependent force where the spin dependence is a sigma X force. Sorry, it's a sigma X operator, okay? So we, and the coupling strength is given by this Lambdicki parameter, which also has the normal mode eigenvector of the particular ion I coupled with the mode M, okay? And we last time went through a formalism on how we can derive an evolution operator that has a phonon part and then a spin-spin interaction part. And we talked about how we can get rid of the phonon part by designing laser pulses in an appropriate way. Right, so this should be a repeat, and right. Now I want to cover a second way in which we use this interaction. In a sense, it's a lot easier because what we're going to do, this is so-called solution number 2, instead of shaping the laser pulses so that the phonons decouple at the end of the interaction, we're going to make an approximation where the phonons are always decoupled. Or a more accurate way to say that is that they're only virtually coupled. And so we can do this by making sure that our laser is detuned really far from all of the normal modes. And then we are exciting the harmonic oscillator modes, but only very weakly, okay? And what happens is the phase space trajectories are little circles, but they're very small diameter, and that therefore limits the entanglement between the phonons and the spins. Okay, so let's go through that math. It's actually a little simpler. So the idea here is, so sorry, that was number 1. Here we go. This is a new slide. You haven't seen this slide yet. So the idea is, sorry, I'm moving pictures around here. The idea is to tune our lasers so that we're very far detuned from all of the normal modes. And here I've drawn only the transverse modes in a given geometrical direction, X or Y. And remember, they're all sort of bunched together. And we symmetrically tune on the upper and lower side bands. That's how we get our spin-dependent force. But we make sure that our laser force is tuned to be very far away from all of the modes. And when that's the case, the displacement operator, the argument, that is the amount of push in phase space, gets really small because the detuning from each mode is much bigger than the Rabi frequency or the line width of these sidebands, if you want. So you can approximate these all as being 0. So that makes the equation for the evolution operator a lot simpler. There are no phonons whatsoever. We only have this spin-spin interaction. And the price we pay is that the spin-spin interaction is a lot weaker than it used to be, because that same detuning we made big is in the denominator of this this icing coupling. Okay, but the good news is that when we set alpha to be very small, this chi parameter, the amount of icing interaction, is proportional to time. So that means the evolution operator starts to look like Hamiltonian evolution, because we have the form, an evolution operator that's e to the minus I t times something, and what's ever left over is we can identify within a Hamiltonian. Sometimes this is called an effective Hamiltonian because there's all kinds of time averaging going on. But this Hamiltonian is basically an icing model. It's an all-to-all connected icing model where the interaction between any pair of ions is given by this nasty formula, which is a sum over all the modes. You know, each mode is mediating the interaction. You have to sum over all of them. Okay. Any questions on the development of that formula? Maybe a review from last time as well.
So Chris, apologies if you're retreading old material here, since I had missed the other ones, but hey, good to see you. But this formula assumes that all the modes are harmonic. How highly accurate is that? And
yeah, good point. We may have talked about that before. The ions are separated by many microns, say 5 microns or so, and the force that we're applying ends up displacing a few nanometers. So it's 1 out of 1,000. And so the anharmonicity of, you usually think, the Coulomb force is highly anharmonic. It's, it's 1 over r squared, but the oscillations from equilibrium are really harmonic. And when we're cooled to near the ground state, you'd be hard pressed to observe any effect of that anharmonicity. So that's an approximation we don't worry about so much. Approximations we do worry about are the residual entanglement with this motion, which I claimed was 0. It's not exactly 0, so you have to deal with that. And there's going to be another subtle approximation. Maybe I'll see if people pick it up in passing. If they don't, I might not mention it. But and I'll give you a hint. The fundamental Hamiltonian. Sorry, here we go. Jeez. Okay. The fundamental Hamiltonian was, this is very slow. I'm sorry. This is the fundamental Hamiltonian, and the only approximation is Lambdicki regime, which is pretty good. But this, there are further approximations, rotating wave, all that other stuff. But we arrived at an effective Hamiltonian using this Magnus expansion. And let me remind everybody that the reason that worked, the reason the expansion terminated, is all 3 and high order commutators vanish, because the Hamiltonian itself, the pieces that don't commute, A and A dagger for a given mode, they commute to a C number. So that means the higher order commutators just vanished. Okay, that's the hint. I'm just going to leave it. And so somebody's going to raise their hand, hopefully, in about 5 or 10 minutes. Okay, sorry, taking forever to do this. There's the nice animation, Hamiltonian, very good. Okay, so we have an all-on-all icing model, which is kind of neat because the long-range nature of this icing model is tunable. These are all laser parameters, right? You have Rabi frequencies, the powers. The recoil frequency of the atom is just a parameter. It's 20 kilohertz for ytterbium. We have a tuning of a laser, so we can tune this icing coupling just based on laser parameters. All right. Now, let me show you a little bit more schematically what this would look like in the lab and why it's working. Remember, we have to have non-co-propagating beams to realize the force, to get the momentum kick. And we have this icing Hamiltonian that resulted from this spin-dependent force. And I'm pretty much repeating everything I just said, but these are the Raman beat notes. Now, the icing Hamiltonian by itself, since it commutes with itself, you might argue it's a classical It's a classical Hamiltonian. There's no non-commuting parts of it. There aren't going to be any phase transitions, for instance, with this Hamiltonian. So the simplest thing to do is make it a little more interesting. So we add a transverse field. Now, how do we do that? And you'll note in the box above that another spectral feature appeared. We add a third laser tone, not the upper or lower sideband, but actually on the carrier itself. And of course, the carrier, the operator flipping spins, is effectively a magnetic field. It's controlled by a laser, and it's actually 90 degrees out of phase from the sidebands. It's because of this eye. Why is it 90 degrees out of phase from the sidebands? Well, remember in the middle of the last lecture, all of this comes from matrix elements of e to the I kx. And I'm not talking about the e to the I kx of the electron in an atom making the dipole approximation. Actually, it is a little bit like that, but this is e to the I kx of the atom moving in the ion trap. And the carrier is the lowest order term, which is 1. And the sidebands are the first linear terms, I kx. So you have that natural 90-degree phase lag, okay? But I mean, who cares about the phase lag? We can actually control the phase of these tones. It's just RF engineering. Very easy to do that. So we can make the effective field be Y or X or any angle between Y and X, okay? But this is more interesting because it's transverse to the XX Ising interaction. It doesn't commute. And I guess this is the simplest Hamiltonian that admits a quantum phase transition. I think that's probably true. I think that comes from Sachdev's book, maybe the first page. The transverse Ising model is the first page of his phase transitions book for a good reason. So this is an interesting Hamiltonian to play with, since we can control B and J just with our knobs in the laboratory. And note again that J is not nearest neighbor. This is not a 1D Ising chain that we all solved in stat mech. It's not even a 2D. It's n-dimensional. It's very high dimensional because it's long range. Now, this is basically, this was pointed out very early on by Ignacio Serac and Diego Porras a long time ago. And our group has really, over the last 10 or 15 years, pushed on this model very hard. So let me now talk about this JIJ, this Ising matrix.
Well, Chris, because no one asked, let me ask. So you're breaking the commutativity.
Okay.
I just want to explain a little bit.
Okay, so what is the question you're asking about?
Well, doesn't the Magnus expansion break down, as you pointed out before?
That's right. Yeah, you got it. So the fundamental Hamiltonian is not this. It's actually this spin-dependent phonon term, and you really have to add the magnetic field to that Hamiltonian and then put it through the Magnus expansion. Unfortunately, the Magnus expansion no longer terminates because now we have a non-commuting term between Pauli operators. So it goes on forever. But it's a power series in higher orders of the Lamb-Dickey parameter. And I'll thank my colleague Jim Freerichs from Georgetown for early on pointing that out and really pushing on it. And the math is just ridiculously hard. I won't even comment on it. But we can, Anna Marie, you probably looked at the same math. This Magnus expansion does it has an expansion parameter that has the Lamb-Dickey parameter, and it also has B over J in it. And as long as the Lamb-Dickey parameter is small, this thing does converge. So I'm a little bit on thin ice because I've always worried about this approximation, but it's true for our systems. We've sort of seen corroboration with just this plain transverse Ising model without phonon terms. On the other hand, we also see that our system seems to have a decoherence, effective decoherence that's larger than we would ever expect. And that could be because of the phonon, the residual phonon entanglement. And so I should put Freerichs' paper up here. He had a long PhysRev A paper. I think phonons is in the title, and that's exactly what it deals with. So yeah, that indeed is another approximation. Okay, this Ising matrix, I mentioned it's long range.
So
And
basically you get a decay model. Yes, that's the conclusion, that we get a multi-mode decay model. That's the Hamiltonian that you are solving,
right.
and that's why it's so exciting. I mean, it's complex, it has chaos, have a lot of complications. So
Oh, you know way more than me about that. Yes, I remember hearing those terms.
but
Right,
if you detune very far, when J's are smaller than I mean, depends on the range of the parameter B that you are going to use, that you
yep,
enter the LMG, or well, the icing part of the
that's
decay
right.
model. So
That's right. That's right. So this Ising matrix, it's a complicated formula. You have to sum over all these normal modes. And again, just to get the eigenvectors, you typically have to diagonalize, a classical Lagrangian of the Coulomb particles and so forth. And it remarkably fits well to an inverse power law. In other words, by tuning the laser beam various places, you can smoothly change the power law of a very well fitted interaction strength with distance. And so I've tried to indicate that in this picture here, where the blue dots. What are we plotting here? This is the power law exponent alpha, and this is the detuning on the x-axis. The detuning scaled to the bandwidth of the sidebands. And that's sort of what's going to matter. Now, the limits make a lot of sense. If the detuning is really small, that is, if you're only coupled to this highest mode, that's the center of mass mode, by the way. If you're only coupled to the center of mass mode, then then you have an infinite range interaction, and alpha is equal to 0. It's an all-to-all coupling. It's also not very interesting because you can usually use mean field to describe this. Not always, but and when you're tuned really far away, what happens is you're spending so little time in the excited state. You're spending so little time making these virtual phonons. Do you remember? I think my first slide, I showed you the back of the envelope picture of a spin-dependent force. You pluck this atoms and then you let them return. Remember that 1/r cubed that came from that very simple approach? Well, that's the largest value of alpha we can do. At infinite detuning, you expect a dipole-dipole interaction. And physically, what's going on is that you're making transient dipoles. That's basically what it is, and you get this distance dependence. Now, the price you pay when you detune really far is, yes, you get a dipole-dipole coupling, but it also gets smaller and smaller, the prefactor, okay? So in practice, it's very hard to get a dipole coupling. And in practice, it's also very hard to get alpha equal to 0 in all-to-all coupling, because if you're tuned so close to the sidebands, then you're making phonons. You're violating the approximation that the detuning from the modes is much bigger than the Rabi frequency of these sidebands, okay? So what we're plotting here is the theoretical power law exponent of the Ising coupling versus the detuning. It's a log-log plot, and you can see that we have sort of control of this alpha from uniform to 1/r cubed by this tuning. Now, in practice, we typically work between 0.5 and 2. 0.5 and 2. And the reason we don't go higher than 2 is that it gets really weak. It's just a very low coupling constant. And as I said before, we don't typically get longer range than 0.5 or so, because then we usually are making phonons. Okay?
But Chris, in that case, you can stereoscopically, I mean, you can use what you explained last time, because for one phonon is easy. Yes, it's multiples of this, that a single detuning, if you are only coupled to the center of mass.
Yeah, that's true. So you end up with a kind of a stroboscopic Hamiltonian. It's not a Hamiltonian model over all times, but if you only observe at certain times and you can calibrate that in the lab, it will be as though you evolved with the underlying Hamiltonian of a very long range interaction. That's certainly true. Yeah. Okay.
So Chris, another question is, I think all of your discussion here, you were pretty much thinking of one band of phonons, just the longitudinal, just the transverse, but presumably I can get more complicated spatial dependencies when I start mixing and matching these modes. Like if I couple them more
yeah,
than
that's true. So in this model here, what matters is the difference in wave vector, delta k, and the way I've drawn it here, delta k will point along one of the transverse directions of motion. Now, of course, you can align the principal axes of the ion trap anywhere you want. So you can couple to both x and y. And that gives you some freedom to have another icing coupling in there. It's like an XY model, XX and YY. The axial modes, I spoke about this last time, we typically don't like to couple to the axial modes because they're very low frequency, they're very hot, they're not in the Lambdicki limit. And so we don't use those. But you're right, I'm talking about only one geometrical band of modes just for ease. Well, here's the John Bollinger slide, and you'll hear more about his work tomorrow in his own seminar. But he works routinely on this two-dimensional crystal, and Anna Maria, of course, is one of the leaders of that collaboration. Now, the physics that they employ is pretty much the same as what I told you about, only they have a two-dimensional crystal. The mode structure is quite different. But this formula I wrote last, it's the same formula for their system. You just have to characterize their modes. They have their own character. And in this paper, I'm not sure which one this is. It's one of these four. I think it's
there's a question from the audience. Why from Nung, who asks, why is the interaction not 1/r6 if phonon coupling is transient?
Why is it not 1/r6?
Yeah. Nung, maybe you can unmute yourself and elaborate on your question.
Oh, I think I got it. So a 1/r6 of van der Waals interaction comes from fluctuating dipoles. You can think of it as originating from fluctuating dipoles. Now, what we're doing here, we have correlated dipoles. There's a phase coherent laser beam that's hitting multiple spins and creating electric dipoles that are aligned, and they're going at they have the same phase. So they're correlated dipoles. And from that, you will get a 1/r³, not a 1/r6. I think that's the main difference. So in one of these papers, they actually measure, if you look on this axis here, there are many transverse bounce modes, they call them, that are, well, their axial modes are what I would call transverse modes, but motion perpendicular to the pancake. And they have very closely spaced modes, and they can, again, Jim Freerichs is, in addition to Anna Maria, has worked quite a lot on this system. And in their experiment, they basically measured the icing couplings using Ramsey spectroscopy, and they can, this might be theory actually. I think these are all theoretical points. And then the alpha exponent.
No, but the dots, I think, are experimental points,
Yeah.
and the
lines are
theory.
The lines are theory.
I think so.
How do they measure each icing coupling, though?
Yeah,
Did they do
I think
Fourier
it's
transform dynamics or something?
So I think what they're going to do is that they are changing the detuning, and depending of changing the detuning, this is the different lines.
Yeah,
Yes.
they're changing the detuning and showing. I don't think that there's any experiment in here, though.
Yeah,
No?
I think the dots are numerics and the lines are the simple power laws.
That's right.
The
lines are
right.
pure power
You're
laws.
right. You are right. Yes, the experiment is there, Ramsey fringes, a separate plot. You're right.
Yeah, it's hard to do that. So yeah, the lines are perfect power laws, and this sort of illustrates the approximation of the power law itself. It's not perfect. In fact, I think a better approximation is sort of a Yukawa potential. It's a sum of an exponential plus an inverse power law, I believe. So they do show, though, for higher detunings, you approach the 1/r³. That would be A is equal to 3. And for very low detunings, this is 100 hertz, only 100 hertz from the center mass mode. It's nearly all to all. Okay. But the physics, the physics behind this model is really the same. So I'm gonna talk now about a bunch of experiments we've done over the few years that are kind of exercising this transverse icing model in a linear trap now. And this is, again, the geometry. We have crisscross beams that they don't have to be counterpropagating. They just should not be co-propagating. And in this case, they're 90 degrees to each, just because of the experimental access we have. And the ions form this linear chain here, and the delta K vector is outside of the plane of these ion trap electrodes. And we press a microscope objective right up against the vacuum window to get this. Okay, the first experiment would be kind of a natural one, and that is, let's find the ground state of a long-range Ising model. That can be tricky. Remember, this is not a nearest neighbor. It doesn't really have dimensionality. We have this all-to-all long-range Ising model. How can we find the ground state? Well, this technique follows an approach called, it's actually a quantum computing approach called the adiabatic method for evolving quantum states. And the idea is to turn on a simple Hamiltonian, in this case, the field, the transverse field, and gradually turn that off and gradually turn on the Ising coupling. And if you do it adiabatically, that means no entropy was gained or lost, and you started in the ground state of the trivial part of the Hamiltonian, you should evolve to the ground state of the more interesting Hamiltonian. So a typical experiment would be to initialize all the spins along the y direction. We do that with carrier pulses, carrier pi/2 pulses. You could do it with microwaves. There's a technical reason we don't. The ions are, the spins are along the y direction. Actually, the minus y direction would be the ground state of this Hamiltonian for B positive. And then we also turn on, for technical reasons, we leave the Ising couplings very low but constant, and we turn on the magnetic field to be very high. At first, nothing happens, and then we adiabatically, or we quote unquote adiabatically, we try to slowly lower the magnetic field down to 0 or down to some intermediate value, and then we stop and measure all the spins along the x direction. Why do we measure along x? Because, well, that's where the order is expected to be, according to this Ising coupling, okay? And to measure along x, we just simply rotate all the spins about the y-axis, about the z-axis by pi/2. I forget, anyway. It's an easy operation. And then we measure all the spins, okay? And here, so the next data I'm going to show is for negative values of J. So all the couplings are ferromagnetic, meaning they want to all the spins want to line up. That's their ground state. And this is a funny way to plot the data. What I've plotted, it's a little hard to see all this. I'll explain it. It's three-dimensional plot. I've plotted the absolute value of the magnetization of the chain. What would that be? That would just be measuring all of the spins and measuring their brightness. So it's an easy measure for us. This axis here is B over J, which is time, because we're ramping the B field down. And this other axis is the number of spins. So the simplest data only had 2 spins, and I wouldn't really call this a phase transition.
You are setting J0 to, oh yes, J0 is 0 is negative. You are, the coupling constant is always negative in that case. You are always,
J's are negative. J's
okay.
are negative here. Yeah, I'm going to return to that comment in a minute. As you can see, the point here is that the transition gets sharper. I guess that's all I want to say. It gets sharper. But look, 9 particles is no thermodynamic limit. So we can't really call that a phase transition. But there are many techniques that allow you to maybe extrapolate this to the thermodynamic limit, called finite size scaling. And there's a lot of numerical recipes for doing that. Now, let's see, how do I want to cover this? J naught, the couplings are ferromagnetic. Actually, they're not. Natively, all the J's are positive. Well, how did we get a ferromagnetic interaction then? Well, this is a closed quantum system. So instead of preparing the ground state of the simple Hamiltonian, we prepared the highest excited state. In other words, we made B negative. You can think of it that way. We prepared the highest excited state of this, and then when we adiabatically lowered B over J, we prepared the highest excited state of this anti-ferromagnetic ground state, Hamiltonian. But we're in the highest state, which is ferromagnetic. Remember, the only difference between a ferromagnetic and an anti-ferromagnetic Hamiltonian is the sign. So we switched the sign by preparing the highest initial state. That's the trick. And because we have a closed quantum system, we can do that. We can just invert the energy spectrum. It's a closed quantum system, so there's finite energy. In a real thermodynamic system, you can't easily do that. The concept of temperature and so forth will make it very, very hard to do that. So that's how we sort of faked this ferromagnetic, we simulated a ferromagnetic type interaction. Now, why did we plot the absolute value of the magnetization? Well, it's because this Hamiltonian has a symmetry. It's called a Z2 symmetry. I should call it an X2 symmetry, I guess. But it has a symmetry that the ground state of the ferromagnetic icing Hamiltonian is degenerate. It's either all spin up or all spin down. They have the same energy. And so if we didn't plot the magnitude, we would be getting a lot of noise. Half the time we'd see all up, half the time all down. So we took the magnitude, the absolute magnitude of the magnetization. Okay.
So Chris,
okay, so
there's a question.
Yeah.
It's from Garrett, and he asks, is there any discrepancy in the population transfer from highest to highest, probably from highest to lowest or lowest to highest, would be less than transfer from, sorry, let me try again. Is there any discrepancy in the population transfer from highest to highest would be less than transfer from lowest to lowest, even if both are adiabatic?
So by preparing the highest excited state, the question is it less stable or something because it's up there compared to starting on the lowest?
I think the question is that it's related to this. Is the adiabaticity different for transferring a highest state to highest?
Oh, yeah.
Lowest to lowest?
Definitely is. I should have plotted the energy spectrum of this ferromagnet. Well, it's an antiferromagnet. Now, near the ground state of an antiferromagnet, I'm going to talk about that next. The gaps are very small, whereas a ferromagnet has very large gaps. And another way to think about that is that when you have a ferromagnet, especially a long-range ferromagnet, if one spin flips, it costs a lot of energy, right? Because you have to add up all the violations of their bonds over every other spin. They all want to align. When you flip one, you're sort of adding lots of energy. Whereas if you have an antiferromagnetic state, then flipping one spin, it costs some energy, but just the nearest neighbors. And in fact, the next nearest neighbors are even more happy. So you get energy back. So when you do the sum, it turns out, the gaps for an antiferromagnetic Hamiltonian are going to be much smaller. So that means it's a lot harder to be adiabatic when you're antiferromagnetic. And that's sort of my next topic. What about the antiferromagnetic Hamiltonian? And in this case, of course, the spatial structure is interesting. An antiferromagnet, the ground state's a Niel ordered state where you have alternating spins. That's very hard to observe in the quantum limit because it's degenerate, up, down, up is degenerate with down, up, down. So in the laboratory, that's just you're not going to see any spatial structure. They're going to cancel each other. But, we have a finite system here and we can measure every spin individually with very high fidelity. So we can just look at them and sort of extract the magnetic ordering. The price we pay is that they're pretty small systems. So this is data from a few years ago, just 10 spins. The power law of this interaction is about 1.12. And we did 2,600 runs of this adiabatic ramp. This time we did prepare the ground state. Let me go back. Sorry, right here. We did prepare the ground state of this part of the Hamiltonian, and that would be all the spins pointing down along Y. And J is naturally antiferromagnetic. So by adiabatically lowering B over J, we should see some signature of the antiferromagnetic ordering of this Hamiltonian. So this is just a calibration pair of figures, all up and all down, bright and dark. And again, we're making these measurements along X, but that's I'm not going to really comment on that. That just means that we change the basis of the measurement or the initialization. Okay, so remember 2,600 runs, and this is what we saw some of the time. So we had 2,600 pictures of this crystal because we did 2,600 single shot runs, and we're measuring the spin state in a single shot. Well, 222 times we saw this thing, 219 times we saw this thing. So that's a total of 441 events out of 2,600. 17% of the time we saw the expected ground state, which is Néel ordered, up, down, and it's inverse, down, up, down, up. Now that's okay. 17% is not too bad, especially when you consider that these two states are only 2 out of 1,024 states, right? There's 1,024 possible states. These two are pretty random. Why are they popping up all the time? Well, they're the ground state, that's why. But at the same time, it's disappointing. 17%, yeah, we weren't very adiabatic here. And the reason is we had finite time to do our ramp, and before we had laser noise inducing decoherence, and we weren't adiabatic. But there's a lot more information here. We have 2,600 runs. We have every single run. And so what else happened? What about the other 83%? Well, about 8% of the time we saw one of these. What do we have here? It's almost Néel ordered, but we see domain walls, right? We see a domain wall here, here. We see a domain wall here and here. And these should all be degenerate. There's a left-right symmetry, and there's an up-down symmetry as well. There's not translational symmetry. Remember, the ions are not equally spaced, but there is a left-right symmetry. So we should see those 2% each. The next highest states, we saw about 1% each have domain walls that are shifted toward the edge of the chain. Again, it's not a uniform crystal, and that's why these are slightly different energy than the first excited states. These are the second excited states. Well, we can plot the distribution of all the states. There's 1024 possible. Is there a question?
Yes, sorry, Chris. These interactions was what alpha? Do you remember? It was very
1.12.
Okay, sorry. Okay, great.
It's about 1. Yeah.
Okay.
Now, for those of you that are wondering, I mean, actually, alpha equals 1 is interesting in one dimension because the energy, it's sort of a boundary for which the energy diverges or it doesn't. If alpha is less than 1 and you have an infinite chain, the energy is infinite. You sort of, one way to say that is that when alpha is bigger than 1, then you sort of have dimensionality. And when it's less than 1, you don't. I guess I won't comment on that because this is only 10 spins. It's not even translation symmetric. So well, let's not worry about dimensionality. It's more like a math problem. You know, we have a lot of energy levels, 1024 energy levels. There's some small gaps. And can we follow those gaps in time? Okay, so there are 1024 states. And this is the experimentally measured distribution of those 1024 states. I've labeled them according to their binary index. So, you know, all up is all ones, that's 1023. All down is 0, and everything in between. So the initial so-called paramagnetic state that's polarized along the magnetic field is largely uniform. It should be about 10 to the minus 3 for each of these. It's kind of there. We see some noise that has to do with imperfect initialization. You see a lot of noise on the all up state, all bright state, and that's a detection problem. What happens is if you have 10 ions and only 9 of them are bright, you more often than not mistaken the dark ion for a bright ion because of crosstalk. So it's just a detection issue. And I think this is probably 128. Again, it's another near power of 2. So you have lots of spin ups, and you kind of see that structure there. Okay. And here's the distribution after the ramp. Again, I showed you these 2 ground states. They are by far the highest populated. So at least they're the most likely state at the end, but you get all this hair, and this hair is very interesting. Actually, it's dynamics. We're getting, many body dynamics in this transverse icing chain. And so I plotted the distribution. So yeah, as I mentioned, these 2 numbers add up to about 17%, these 2. Let's now plot the distribution of all these states ranked by their energy. Again, the binary index is sort of arbitrary. It has almost nothing to do with energy. And when we do this, let's see, we actually have 2 different ranges in this plot, and it's a little hard to see all the data. Sorry about that. But we largely see what looks like kind of an exponential distribution. Anyway, it seems to generally decrease, but there are definitely some states that just aren't present at all. And you see the ground state here. It's there are actually two of them. They're degenerate, and there's also a gap to the first excited state. And then you can you see all the other states up there. It's sort of a mess. And one thing you can tell a little bit here is that as we increase the range of the interaction, the gap gets smaller, as expected. When you have a long range interaction, then we expect antiferromagnetic gaps to really to shrink. Maybe it's more interesting to plot the cumulative distribution of energies here. I've always found this kind of interesting because they're almost exponential. Why would they be so what am I plotting here? This is the cumulative probability of occupying a certain state after that ramp. And it fits, there's some steps here because we have quantum levels and gaps and so forth, but it's pretty close fit to an exponential. And a good question is, why should it be exponential? Very fundamental question. Maybe David Hughes's lectures address this a little bit. We only have 10 spins here. How can they thermalize? It's a closed system. Well, there's a lot of entanglement going on, and the way we think about it, I'll talk about this a little bit, I guess. The model of thermalization in a closed system is that with entanglement, you get to have any subsystem thermalize with the rest of the system. And that's sort of formally how we think of thermalization in a closed system. And some very deep math of why you might expect that to be exponential, but I think I'll just leave this here alone and move on. Very similar data here with 14 spins instead of 10. And now we have 16,000 configurations. And you can see right away, we paid a big price just by adding 4 more spins. We've lowered the probability of success from 17% down to, I don't know, like 3%. It's because the gaps got even smaller with the bigger, the bigger system. Okay. That looks like a repeat. Okay, so this is sort of a taste of kind of the flavor of some of these quantum simulations we can do in our system. And, they're long range interactions that are very interesting. The entanglement structure is certainly interesting. And even indirectly, you can identify certain aspects of the entanglement. Now, I wish I had time to talk about all of these topics. Some of them.
Just one question for this, you were always using a linear ramp, or you were trying to optimize the ramp?
No, in fact, this reference Phil Risherm, we tried to optimize. Did I get that right? Yeah, we tried to optimize the ramp. We tried exponential. We tried linear. The problem with exponential is that, well, the problem with any ramp is that you really only need to be slow when the gap is really small, and the gap is not small everywhere in the ramp. Certainly at the beginning and the end, it's probably not. And it's a little bit of a circular problem. You don't know where the gap is small. If you did, then you would have already solved the problem. So but
in the system you do, because you have simulations where it is, no?
Yeah. So we sort of cheated and knew where the small ramp was, and we would slow down the ramp then, and it would work better. Mm-hmm. But there are ways to. There are other ramps that are interesting. That I think it's 1/1 plus t, which will keep the same adiabaticity parameter the whole time. But 1/1 plus t has a long tail. It takes forever at the end there. So there was no real good solution here. And I'm not an expert in adiabatic quantum computing, but this is related to the reason adiabatic quantum computing is not seen to be all that powerful. I shouldn't even say it that strongly. There may be cases where you have a gap the whole time, but it's a little bit circular. You can't know without solving it. Actually, this picture here, we did spectroscopy of the many body states of our system. The ground state is scaled to 0 here, and as a function of B, we can see the minimum gap from the ground state. Which, sorry, it's hard to see this. There's a ground state at 0, and this first excited state, you can sort of see that it has a minimum gap at this value for some value of j, it's roughly b over j of about 1. And how did we get this data here? Well, here we ramped the Hamiltonian down to a certain value, and we applied radio frequency and directly measured what we got. Remember, we're measuring every spin and its state. We can map out these eigenstates with okay signal to noise. Okay, so again, I'd love to talk about a lot of these. There are some in the audience that know more than me, like about time crystals. Francisco, I'm looking at you right now, Mr. Time Crystal. You should be lecturing here. Okay, but I will talk about a few things. One maybe that will tie in with David Hughes's lecture a little bit. And there's an interesting concept called pre-thermalization, which to me, what it means is that there are time scales in the, sorry, there's supposed to be an animation. I guess I'll just show you the whole thing. Well, no, I won't. There are two time scales in some of these problems because an energy gap is very small. And it takes a long time for that energy gap, in a sense, to fully partake in the dynamics. But let me just give you an example, an experimentalist view of pre-thermalization. Here we have a chain of, I think, 22 spins, and we apply an XY model. I didn't tell you how we do this, and I won't tell you how we do this, but it's an extension of what you already know. It's a XY sigma X plus sigma Y, which is also a flip-flop model. So this one conserves the number of excitations in the chain, right? But you can have hopping. You know, an excitation can hop with no energy penalty. So this is a long-range XY model with the exponent of 0.6, and this is just a calibration run. These are where all the spins are. So at time equals 0, we prepare this state. So spin up, everybody else is spin down. So what's going to happen, of course, is that this excitation, if you think of spin up as an excitation, it's going to move throughout the chain. And what's interesting is that at a presumably long time, JT is 36, and there's a 2 pi in there as well. That means we've had lots of chances to have the icing interaction. It's long range. You'll note that after we measure at JT of 36, we still see only one excitation. Every single shot was one excitation. This is an average picture of many, I think several hundred, maybe about 1,000 shots. And you can see that the excitation made it through the entire chain. It made it all the way to the end, for sure. You can see a little bit of probability there. But the center of mass of that excitation barely moved, even after 36. That might be a little surprising. It just takes a long time for this long-range Hamiltonian to thermalize. And if you plot now the time evolution of the center of mass of the excitation, I've scaled it to be between -1, which would be where it started, and +1, which would be the end. And we expect by symmetry, the equilibrium value should be 0. We should have an equal superposition of all 22 excitations. And at least to our experimental error, we don't see any signal, signature that we're going to thermalize. It looks pretty flat, even at sort of long times. We can't go much longer than 36 because there's known laser noise that effectively makes the spins decoherent. So we don't take data after that. But there's a clear bias here, and this is a signature in a small system of pre-thermalization. If you look at the energy, the distribution of energy gaps, you can see there's this one pair of states that always has a tiny gap. And that's certainly true at lower values of alpha, where we have very long range interactions. So the lower alpha is, the more we expect to see this pre-thermalization. This theory here comes from Gong and Duan's paper from several years ago that look at, I believe, I'm not sure what, it must be the same order parameter, the position of the excitation. Now, it's a log plot here, though, in time. So you can see that something happens, things seem to sort of stabilize. That's sort of the pre-thermal regime. And then finally, things thermalize, but it takes an awfully long time. And this plateau is kind of interesting. And
yes, Chris, this is fantastic because this is exactly what David was talking last lecture. So it's the perfect example.
I'm sorry to say that if you look at our data, I mean, what does the data correspond to? Maybe up to here. We just, it's the bane of experimentalists. I mean, people like Anna Maria and David are always asking us, well, can't you go out, infinite time? And, these non-thermalization studies, in time crystals, many body localization, that's the problem. You really need to go out to super long evolution times, and we're not there yet. It's the same challenge of quantum computing, actually, in most experimental platforms. But we think we can claim that there are some, signatures here of pre-thermalization in a system like this. Okay, what about MBL, many body localization? It's another, to me, like pre-thermalization, it's another example of how systems do not thermalize. Now, closed systems, again, based on your lectures from David Hughes, you know that closed systems formally do thermalize if they're not integrable. Because of the entanglement in the many-body system, you can think of it that way. And again, when you trace over subsets, you get you get effectively thermalization. Well, let me just go through experimentally how we might observe something called many-body localization, which you just heard of a few hours ago, I guess. In this context, again, you have to give me a little bit of benefit of the doubt. We only have 10 spins, so it's a pretty darn small system. So here's what we do in the laboratory. Instead of preparing an AFM state, we actually jury rig it. We just initialize the spins in a staggered order. We have a little poke beam that allows us to individually address them. And again, we're going to be measuring along the x direction of the block sphere. So this is sort of like an infinite temperature state, if you want, right? It's down plus up to the nth power, or maybe down plus up, down minus up, down plus up. So apart from phases, this is an infinite temperature state, even though it has coherence in it. Okay. The next thing we do is we quench this system to our usual long-range transverse Ising model, this time with a transverse field along Z. We do this with a simple detuning of the spin-dependent force, notwithstanding the approximations Anna Maria was so kind to mention that Jim Freerichs also worked out. Let's forget about those. But we also add a site-dependent magnetic field. And this we do with what we call a poke beam. And AC Stark shifts the qubit just a tiny bit. And this is going to be the disorder that allows many-body localization. The conventional theory of many-body localization is that you have to have disorder in addition to having this entanglement structure, this type of interacting system. And we're going to sample this disordered field from some distribution, a uniform distribution measured, parameterized by W. And then we measure the spins along Z. We like that in the lab because that's the lab frame, Z, bright, dark. So it's actually conceptually a pretty simple experiment. The problem is we need to sample many realizations of this disorder, and then many different variances of the disorder. And for each distribution of the disorder, we have to sample many instances of that disorder. And we measure each spin in this 10-spin chain. Okay, so that's the setup. Now, what would we claim as a signature of MBL? Well, here we're looking at there's only 10 spins. We measure every one of them as a function of time in this, sorry, let me go back here. In time exposed to this Hamiltonian, but before measurement. And we see that, again, half the spins were up, half the spins were down. This has no disordered field at all. W is equal to 0. And we see there's evolution. We do have a transverse Ising model. Is an XX term and a Z term. And so there's competition between the two and we get dynamics, but after some amount of time, each spin is sort of depolarized. We're measuring sigma Z and we get pretty much 0. As we add disorder, though, you can clearly see that the spins sort of retain memory of their initial state. So from 1, 2, 3, 2, 4, 6, and 8, when the variance is, or the width of the distribution of disorder is 8 times the Ising coupling, we find that the states sort of they localize. This is really the kind of the signature. And with 10 spins, Shankar Dasarma's group did exact diagonalization, which is It sounds pretty easy, but again, this is a long range interaction, so it's not super trivial. And again, our dynamics is borne out in theory. We see kind of qualitative agreement. Now, what we're going to do now is, instead of plotting for different values of W, these entire curves in time, we're going to plot the Hamming distance. That is the distance from the initial state as a function of time. And again, at 0 time, you are in your initial state. There is no distance. And Hamming distance is basically the number of positions where the spin has flipped. And it's scaled to the number of spins. So this will vary between 0 and 1. Well, if it's thermal, then it should be a half, because half of the spins are up, half are down. It's sort of an unbiased state. But again, as we add disorder, we see that there's memory retention of the initial state, and that's the clear signature. And furthermore, we can sort of arrive at something akin to a phase diagram, but I hesitate to call it a phase when we only have 10 spins. But as we increase the disorder strength, we clearly see different behaviors of the steady state Hamming distance, the memory retention. Okay. When it's in the MBL phase, it has more memory retention. And finally, this is even looking further into the data. As we repeat this entire experiment while varying the range of the interaction, we see that this is once again the steady state Hamming distance. We see that it becomes more localized for larger alpha. That's the message of this plot here. Okay, sort of predicted by theory. So again, we would claim these show the signature of MBL, the ingredients needed in a many body entangling Hamiltonian plus disorder. All right.
Chris, the theory included any decoherence, or the theory was pure Hamiltonian?
The theory here was no decoherence.
No decoherence. Okay.
Yeah, that was pure Hamiltonian. And yeah, we spent a lot of time trying to match it more perfectly, and it's a tricky thing. The decoherence models of laser noise. There was no systematic way to have these things fit a little better. Anyway, Shankar was kind of pleased. He thought that it justified the claims of this memory retention with disorder.
Yeah, they look similar.
Okay, let's how much? Oh boy, we're running out of time. Okay.
30 minutes more. Mm-hmm.
Oh, 30. Well, that includes questions, though, right?
Yes, exactly. Yes. So yes, like 15 plus.
Okay. I really want. All right. I'll just. It's slow to breeze through these, but I'm going to cut through these simulations. I know you're all very interested in that. I want to talk a little more about a simulation in the. This will be a quick slide. It's actually kind of fun. This is a simulation of quantum scrambling, a litmus test for quantum scrambling, but it's not using solution 2 to do this quantum simulator. It's using gates.
Just to check, I only see a blank screen. Is that okay? There it is.
Yeah, it's fine. So here's the idea, and this was like many of our experiments. Norm Yao at Berkeley and his group, they knock on the door and say, "Oh, you should do this. This is very cool." And then after a year or so, we do the experiment. And then after another year, we write a paper on it. That's been going on for, I don't know, about 5 years now. It's like clockwork, though. Right now, we're working on a way to verify some verification circuits for quantum computers. And I'm not sure exactly what's next. I need to bother him on that one. But this is an example of the kind of collaboration that I love, because before really being introduced to this topic, I had no idea what quantum scrambling is. It has, in a sense, it's more than entanglement. It's entanglement at all depths, if you want. It's one way to look at it. And so a quantum scrambler is a property of a circuit or a unitary operation. Maybe it doesn't have to be unitary, but certainly unitary operations can scramble, others don't. You can have entanglement without scrambling. Okay. So it's sort of an extra degree of freedom if you want to think of many-body quantum systems. And remarkably, it's relevant to information evolution in black holes. Black holes are thought to be really fast scramblers. If you put a qubit in a black hole, it gets scrambled with the whole system, sort of by definition. And again, this results from certain models of black holes in linking quantum and gravity, which are way beyond my understanding. But the concept of a scrambler, I can kind of get my hands around that, especially if it's only a 3-qubit scrambler. So again, with some of these experiments, you have to kind of set your eyes a little low, set the bar low. So 3 qubits. I mean, 2 qubits is not enough, because if 2 qubits are entangled, they're also scrambled. So entanglement and scrambling are the same thing for 2 qubits. But 10 to the 20 qubits, that's really interesting. But 3 qubits, at least, you can tell the difference between a scrambling unitary and a merely entangling unitary. Okay, and this circuit remarkably will test whether that unitary U scrambles or not. So what are the ingredients here? We have 7 qubits. This is a quantum circuit, time-space diagram. The space is vertical, time going from left to right. And we prepare an initial state, some unknown. It actually is known, but it's an arbitrary initial state in the first rail, and the other qubits are all zeroed. These blocks create entanglement. This one between the 2nd qubit and the 5th qubit, here between 3 and 4, here between 6 and 7. And then we implement our unitary. And the tricky part is we also have to implement U dagger. Actually, I think it's U star, but let's not go into details. It's sort of related to the time inverse of U. And actually, with this connection, I won't talk about out-of-time order correlators, but this is an interesting observable where you evolve a quantum system forward in time and then backward in time and make a correlation between those two. It's really hard to do in a quantum system. And you can sort of see that we have a little bit of that flavor in this circuit here. An OTOC, an out-of-time order correlator, also is related to scrambling. It can be correlated to whether something scrambles or not. A key difference, however, is that if in this circuit, if U and U dagger are not exact opposites, or if we have decoherence, then we will have a separate indicator of that in this circuit. And let me tell you what I mean by that. There are many ways to look at this circuit. One of the weakest ways, and it's not scalable, is that we do a post-selection based on measuring a Bell state in any one of these pairs. It doesn't matter which one. But when you measure a Bell state on, say, qubits 3 and 4, you get to say, okay, I'm now going to measure the last qubit. And it turns out that if and only if U scrambles, this qubit, the first unknown state here, gets teleported to that last rail, if and only if U scrambles. It's kind of amazing. And again, Benny Yoshida at Perimeter really kind of first put this together with Norm in their groups. Now, there's a way to make this scalable. Instead of doing the Bell measurements, you can put actually a Grover circuit that concatenates things. And I won't get into those details, but you can scale this up to bigger systems. So the sleight of hand here is that this evolution operator, that's our black hole. And here's our inverse black hole, if you will. Okay, so I don't want to say we're making black holes. We're testing whether a unitary scrambles or not. And the connection to black holes is kind of interesting. Now, I didn't show you what U was. I forgot to put that slide up. It's a standard 3-bit circuit that has some variables in there that allow us to know that it's scrambling or not. And in fact, we show that it does. And so, again, this is a little bit of a high-level slide. Too many pretty pictures here. This is a picture of an actual wormhole and 2 actual black holes. And so, apparently, Lenny Susskind tells me that this teleportation process is akin to traversing a wormhole. Anyway, I always have to laugh when I say that because it's just crazy. But there is apparently a deep thought of connection between entanglement and teleportation through wormholes on the quantum side. Sorry, entanglement and teleportation on the quantum side, and wormholes, and traveling through those on the quantum gravity side. It's really amazing. And one thing that Lenny has told me is that if we could repeat this circuit with maybe 100 qubits or 200 qubits and make a 50 or 75 qubit unitary, he expects there might be some kind of emergent phase that you could see. And again, it's a complex system, but at least it's not a real black hole. So the moral here is that it's just amazing with these many body quantum systems that you can touch areas of physics that you know nothing about or you wouldn't expect. And so to me, I think this is the most beautiful thing about the field of quantum information. And yes, quantum computing. I'm an atomic physicist, but this is as far removed from atomic physics as you can get. Another application using circuits involves error correction. And again, this is a whole topic unto its own. Could have 3 lectures on just error correction. And I'm just going to skip right through it. We have recently implemented a 13 qubit code and showed that the super qubit we get in the end is, in a sense, less noisy than the physical qubits we started with. So that's a sort of a recipe for fault tolerant control. And again, this paper is on the archive if you're interested. It's going to appear in Nature like next week, actually. All right, we want to scale up.
Chris,
yes.
Because it's been in the news, the Google team also had an error suppression paper in Nature today, I think, or this week. Do you have any quick comments on that?
Oh, is that right? Interesting. Well, so error correction is a very interesting topic. It's a little bit loaded. I think in the trapped ion platform, we don't really need error correction yet because gate fidelities can be as high as 3 or 4 nines. And that means you can go ahead and use a few hundred qubits without ever using error correction and probably get to your solution. Okay. In superconductors, they have no hope of getting 4 nines of fidelity natively, unless there's some physics breakthrough in some material, I guess. Maybe we're counting on that, but they are around 99% or something like that. So with 99%, you can only really do, you're only using 10 qubits effectively if you only have 99% fidelity gates. So in superconductors, we have to think of error correction right away, even from the beginning. But the problem is that native errors are not so great. So the overhead is not 13 to 1, it's more like 1,000 to 1. In some cases, in photonics, linear photonic quantum computing, it's 100,000 to 1. So I'm not sure what the breakthrough is, but I don't think they deployed 100,000 qubits. It could be a theoretical breakthrough on maybe improving the thresholds of these things. I'm not sure. Is it even active error correction at all? I'll look at it. I just wanted to show this slide. One way I want to talk for a few minutes before I quit about scaling. That's the big point. You might be disappointed at 10 qubits. I'm disappointed at 10 qubits. We want to move to thousands and tens of thousands of qubits. The good news is that with atoms, we don't worry about manufacturing. We don't worry about defects in manufacturing. An atom is an atom. If they're the same element, same isotope, you have perfect replication. We don't worry about that. And that's why they make great atomic clocks, as Jun Yi noted in last week's lectures. Well, why don't we do 121 ions instead of just 10? Well, turns out the vacuum needs to be really good to hold on to huge ion chains. So many in the community are going to cryogenic vacuum chambers, not absolute 0, but 4 Kelvin. So at helium temperatures, which is a lot easier. And this chain actually, there's a gap here. There's a different isotope of ytterbium. This gap stayed in that same position all day. It was about 12 hours or so. And so that means there was not a single collision with the background gas in the system because the vacuum is so good. So we sort of know this is, I commented earlier on the engineering needs in ion traps. This is one of them. I think if you want more than 100 ions or so, you really should go for a cryogenic system. And this is sort of, well, some automatic loading procedures and so forth. If you really want to scale up, you got to get rid of this thing. I love the students, but it's the stuff on the left here that needs to be reliable and compressed and so forth. This experiment has exactly 2 ions in 2 separate chambers where we photonically couple one to the other. I'll talk about that very briefly. But we've had a lot of progress in the scaling of this type of a system. And without much exaggeration, everything you see on the left here has been put in this box. It's about 1 meter cubed. The box is closed for months at a time, and everything we need to adjust, we can do autonomously and remotely. All of the adjustments. And what's in the box is, again, a very adept optical system, the Sandia chip trap I talked about before, and these counterpropagating Raman beams. And if this is starting to look like an engineering project, it really is. We were funded largely by IARPA to do this, and that afforded us to work with companies who could integrate some very advanced laser and optical products for our uses. Harris makes this 32-channel AOM for lithography. They happen to work at 355 nanometers for lithography. We use 355 nanometers for ytterbium Raman to address individual ions, and they love this. It's another application of their device, and we had them engineer it for our uses. That's very expensive to do, and we were luckily, funded by IARPA and more recently the NSF STAC program to do that. But it looks like engineering, and maybe companies should do this. And this is really where I want to talk very briefly about IonQ, which is a company in College Park that has built 5 generations of quantum computers that look a lot like this system here, only they're a lot better in the software side of the stack. A couple systems 2 and 3, we've built 5 systems. These 2 are actually on the cloud servers right now at Amazon and Microsoft. And Google Cloud Platform, GCP, just got involved as well. And you'll notice, some of these are hardware competitions, and they're featuring our hardware in their cloud service. So that's very interesting. Again, these cloud servers have relatively low qubit counts, but very low noise. And they're giving Google and IBM a run for their money because our systems are outperforming them pretty much at every pass. For less than 20 qubits or so. And again, Google and IBM can go ahead and put 50, 100 qubits out there, but they can only execute a few ops before things fall apart. So my question is, why so many qubits? Maybe they should work on the fidelity a little more. Well, anyway. So this is an example of some of the automation on some of the IonQ systems. It's all done automatically. Here's a micrograph of that ion trap chip, and we're loading ions one at a time in real time here on the TV. From this loading zone, the atoms come from the back and they get shuttled one at a time over to this zone. They're even zigzagged, and we wanted 24 qubits exactly. When we got to 24, we stretch out the chain and then we refocus the optics, and now we're ready to go to do quantum algorithms. You'll note they're roughly equally spaced because this is a quartic potential that allows us to do that. Boy, I don't have time to go through some of the results from IonQ systems. Water simulation. Again, they're small quantum computations, and I really feel bad about it. But I do want to save time for questions, so I'm just going to put like 1 or 2 more slides.
Yeah, that's good, Chris. Perfect. Thank you.
Up at the end. I didn't talk at all about photonics, but one of our, 2 more pretty pictures will be done. One of our calling cards with ions is the ability to scale up using a modular photonic interconnection. So you could imagine having individual ion traps here, maybe even on a single chip, and they get coupled to photons. And I didn't have time to tell you how that works, but it's been demonstrated over a decade ago. And by having optical switches and detector arrays, we can entangle in a modular way ions from different traps over distances. Now you might argue again, why don't you have 10,000 qubits? And I think the reason we don't have 10,000 qubits right now is that we don't have the low enough errors yet to enjoy those 10,000 qubits. I think the story about ion trap development is that we're increasing qubits and decreasing error at the same time. And that's a really hard thing to do in general. Usually when you add qubits to a system, you're just opening the door for more noise. But with atomic systems, I think we're the only platform, atoms, natural quantum systems really is the only way to scale. I just don't see any solid state system being able to scale in a quantum computer. That's a very strong statement. I think there's wonderful physics to be had. And I think many universities and government labs and even companies like Microsoft will be funding some of this wonderful condensed matter physics. Maybe we can find a natural error correcting qubit in a material. That would be amazing. But the natural systems on the atomic side, these are only limited by engineering challenges going forward, because the quantum systems themselves are fundamentally replicable, and we can deal with them. So the answer to why we're not yet at 10,000 qubits is that we don't yet have a part per million error. We're going to need to do some error correction to get there as well. And more error correction demands even more qubits. So to get more gate operations, we need more qubits. And that's sort of, I think we will, push through this so-called quantum advantage line. We may never get to RSA decryption. That's a really challenging one. But, if we can get poke far into this domain, maybe that's not too far behind. Okay, I'll quit right there. And I'm sorry I talked fast and rushed through way too many slides.
No, it was fantastic, Chris. Thank you so much. Excellent. So please, now the room is open for questions. Yeah, I imagine the students are tired because we have a lot of 4 lectures today.
I'm sure.
So what do you think is the next? So you are saying the cryogenic was fundamental for incrementing the number of qubits in the ion queue. You plan to be cryogenic too, or?
Yeah, actually, we've built 5 generations, and we're building the next 3 right now, and they're all cryogenic. But we actually look forward in the long run of actually going back to room temperature. And the reason is our systems, the vacuum chambers are getting smaller over time. Jungsang Kim, who's the co-founder of IonQ and my colleague here at Duke, he's figured out a way to, let me find this chip here. He's figured out a way to seal the vacuum right on the chip with a little thing, not much bigger than the size of a $50, and it maybe a centimeter thick. And the vacuum windows are all there. He's worked with cold quanta on that one, actually. And the reason we like room temperature is that that's a little small unit, and this optical, modular type of architecture, you don't need more than 50, 100 qubits maybe on a single chip. I don't know, but I think there's room to get another factor of 50 in vacuum at room temperature by using the right materials. And so there's an engineering push there. 4 Kelvin is not a big deal. We work with Montana Systems. They have closed cycle helium systems. They vibrate a tiny bit, but they've really done some great engineering in minimizing that vibration so they don't affect our systems. So we use some of those systems in our later IonQ devices, but we're hoping to get back to room temperature.
Okay, great. Makes sense. Yes.
There's a question from Garrett. Do you just want to unmute yourself and ask?
Sure. So I had a question about the loading of the ion traps into this, I guess, the 24 qubit long chain. I was wondering, what difference does it make that you have to shuttle the ions one by one into the trap, as long as it's done slowly enough, and they're going to form an ordered crystal anyway? Why don't you just flood the potential with all the qubits?
Really good question. I'll answer in 2 ways. The first way is that the way we load, you'll notice that this black here is actually a hole. It's a hole right through the chip. And you can't see it, but there's a tiny 3 micron diameter hole right here as well. You can't see it. We actually load the atoms from the back. And the reason is these atoms are metal. It's ytterbium metal. And if we evaporate a bunch of neutral atoms on the front of the chip, it's going to short the electrodes. Kind of a stupid thing, right? Okay, so we load from the back, but we can still load directly into this zone with a big puff of atoms. It turns out that it's not as reproducible to load a puff, and it's hard to load one at a time from the atomic source. We have to heat it up every time. Whereas here, if we just turn the flux down to 1 per, I guess behind your question is why bother shuttling? That's a lot of work. We're going to have to shuttle anyway as we scale up. I didn't talk about that, but we're going to have multiple zones on a single chip where we shuttle back and forth. Honeywell's doing this now. Dave Wineland and I started thinking about this about 20 years ago. It's called the quantum CCD architecture, and we're doing that anyway. And Sandia National Labs has really pioneered a lot of those programs to do that. We have 100 electrodes here. It's actually not hard. Shuttling is not hard as you think. Once you've got the ion loaded, they're nailed to the electric field zone, and you can really move that along. These 100 electrodes have voltages that we have to apply. It's a little bit of a pain, but they're done with FPGA electronics in ways that we can deal with that.
Cool. Nice. Thank you.
I'm sorry, a question. So you talked about being able to realize, sigma x Hamiltonians earlier, and also in your previous talk. So what kinds of gates are you able to actually implement in the quantum computers that you just talked about?
It's actually the same thing. Yeah, I think I talked about it in the last lecture when we remember solution one was to synchronously decouple those phonon modes, and we end up with this type of a truth table in the quantum gate. This is actually an XX evolution at the end of the gate. So it's as though we applied an XX Hamiltonian, and that's indicated by this equation down here. So it's the same as the quantum simulation, only here it's sort of synchronous. Only at the end of the gate did you realize an XX entanglement. That make sense?
Yeah, that makes sense. Thank you. And can I ask another question? So it's like, how large is the largest quantum computer that you have now? I mean, how many qubits do you have that you can actually do quantum computing with?
One slide I didn't show in my current deck here is something from a few years ago. We did a quantum simulation with actually 53 qubits. It's funny because that was the same number that Google used in their supremacy later that year. And this was a quantum simulation involving 53 qubits in a room temperature system, actually. The system I showed you, the linear trap. Now that's we do in principle have universal control over this system, but it's not with 53 individual beams. For this experiment, in fact, we didn't need a single individual beam. We were, this is with a global beam, so the optics was a lot easier here. Now, in terms of individual addressing, on campus, we're operating a 32 qubit machine right now, although we're using it with less than 25 right now. It turns out when you put too many ions in the trap, they become soft. Some of the modes become very soft, and we need to do sympathetic cooling. We need another species in there, so we're sort of working on that. And the same is true at IonQ, I would say. They're, the ones on the cloud, the commodity systems are now, I think they work with up to 11 qubits, even though there's 32 beams. Our fifth system that's sort of under development now is being used on jobs, not on the commoditized cloud, but with certain partners. And we're playing with up to 20 qubits, something like that. So I guess it depends on how you count. The moral here is that if you have some number of qubits and you really claim to being using those qubits, your error better be 1 minus 1 over n squared. So if you have 10 qubits, you better have 1% errors or better to do typical algorithms. If you have 30 qubits, you better have 99.9%. So you can see the problem. As you add qubits, you need to do better on the errors. So throwing 53 qubits out there without 4 nines of fidelity, you're not going to be able to do generic computations. Simulations like this, or the random circuits that Google ran, those are exceptions.
I see, thank you.
Excellent. So we have one chance for one last question.
Can I ask a question? Hey, Chris.
Yes,
Francisco, hey, go ahead.
You mentioned that there was this idea of the architecture being coupled with photons.
Yeah.
Since you didn't have time to talk during your presentation, can you elaborate a little bit more on what are the challenges?
Very briefly. Let me just show one slide here. So the idea here is that, and again, 1 + 1 is sufficient. So 1 ion over here, 1 over here, and the goal is to entangle these two guys. Well, it turns out we can stimulate a single photon to come out of a single atom. That's not a surprise. And we do it with a laser pulse that's much faster than the line width, than the excited state lifetime. So this is a picosecond pulse, and the atom emits a photon in 10 nanoseconds. So at most, we're going to get one photon. You can't get two photons there. You can get zero, though, because we have to collect that photon. So it's probabilistic. And actually, I'll stay with this one. Sorry. Shoot, I have all this animation here. I didn't want that. So this photon, when it decays, its polarization can be entangled with the qubit, or its frequency, or its time band. I mean, there are many ways to encode, but let's take polarization. Well, the magic is this 50-50 beam splitter. You might know that when you put two photons on a beam splitter and they're mode matched and they're the same polarization, they always go the same direction at the output. What we're going to do is we're going to wait for a correlation event between the two outputs of the beam splitter. But I just told you that never happens. But the photons are not necessarily mode matched. They're entangled with the spin. So they could be different polarizations. And so by detecting appropriate pairs of photons back here, you destroy the photons, you've collected them, but you project the two qubits in an entangled state. So this is not carrying information. It's not a gate. It's just hooking things up. It's making a singlet state. And with that singlet state, this ion can be nearby other ions. You can teleport gates using that entanglement. It's a resource. And that's basically the idea behind photonic interconnections over a large distance.
So I guess, should I think of this as kind of like at the start of the computation, you're able to build a lot of pairs and then use them during the computation? Or
yeah, I think you're going to have a factory, because once you use them, they're sacrificial. They're done. I don't know if I have any slides on that. Yeah, I mean, so here's how you might do it with two different species, which you need to do, by the way, because you don't want that pulse laser hitting the memory qubits. So when the red ones are entangled, you get to use them up by entangling them with others. Then you get to re-entangle them and use them again. You'll probably have a whole battery of these, a factory of making them. And you can also make them synchronous by having a buffer type structure, because they generate, the entanglement is generated randomly. You don't know when, but by having a buffer, you can make it synchronous and use that as your resource.
Awesome, thanks.
Yep.
Excellent, great.
Thanks for asking that. I'm glad I was able to at least color that a bit. Okay, well, thank you all.
Perfect, Chris. Thank you so much for the fantastic lecture.
Thanks, Chris.
At some point, we will ask you for your slides to put it in the webpage. Yeah. So, and I'll see you tomorrow. Our last day of the week, actually. That's
okay. You have a sum up period at like 3 o'clock, right?
Yes, exactly. Can you join us?
Yeah, I'll try to join you. So 3:45.
Oh, that would be fantastic.
Right?
Yes.
Okay, good. Love to.
Thank you.
Good seeing you.
Bye-bye.
Yep.